So here's these are coffee filters from Mr. Coffee or whatever. Um, when I take one of these coffee filters and I crumple it up and drop it, it falls fairly fast. But if I don't crumple it up, you can see that it falls much more slowly. So air resistance, not surprisingly, you would have guessed, I think, that it depends on the cross-sectional area of the object. Now what happens, so what's going on? Why, there's a gravitational force, but what exactly is happening? Why is the air able to exert a force? Think about what air looks like at the microscopic level. Yeah, it's running into air molecules, isn't it? It's just plain running into air molecules. And in fact, the air molecules are moving around randomly. So some of them at any given instant, some are moving up and some are moving down and sideways. But what's going to happen preferentially? It's going to run into the ones that are moving up. So momentum transferred from the air molecules moving up to the filter, slowing it down. Whereas the ones that are moving down, they're getting away from it. So preferentially, it's running into air molecules that are moving this way, and that's where the force comes. That's what's going to slow it down. Now, so what actually happens here is kind of interesting. When we talk about things moving under the influence of air resistance, so a coffee filter or a parachute jumper, what happens to their speed is interesting. If we plot v sub y versus time, so if that's time, this is v sub y for the crumpled up coffee filter, something that isn't much affected by air resistance, but is just affected by the gravitational force. What's it going to look like? What would a graph of the y component of velocity look like versus time? So it starts at 0 because we're releasing it, right? And then I'm hearing straight line, but I'm hearing both positive and negative slope. So, well, this is v sub y, so it's the y component of velocity. So is that a positive or a negative number for this? Okay. So something like that. And what does this have to do with the momentum principle? Well, in every delta t, so we have delta p sub y is f net y delta t. And if this is a constant, this gravitational force, this is going to be a minus mg, isn't it? That means that for every delta t, we're going to have the same delta p sub y, right? And so the same delta v. So for the first delta t, we get that much of a decrease. And for the second delta t, we get that much of a decrease again. And for the third delta t, we get the same. So here's our delta, It's always the same. So straight line, right? What happens under the influence of air resistance, though, so this is constant gravitational force. Air resistance is, although initially something starts to speed, it speeds up for a little while, but then it actually falls at a constant speed. And you'll get a chance, not next week because I think there isn't a lab next week, but the week after, to play with this in lab. And so what we see is something like this, that it starts to speed up for a while, but then actually it reaches a constant terminal speed, and it falls at constant speed, and that's not real fast. So let's think just in terms of the momentum principle about what's going on here. So we'll start with, initially, here's our coffee filter, and it's at rest. When we release it, the only force acting on it is the gravitational force because it's not moving. So we have the gravitational force. But after delta t, it's picked up some speed. So now, let's make the coffee filter some other color here. So now the coffee filter's fallen a little bit. The gravitational force hasn't changed. But because it's now moving and running into those air molecules, there's an upward force due to the air, right? The air resistance force. And so we'll call that F air. And we picked a snapshot here where the upward force due to the air is smaller than the gravitational force due to the Earth, so the net force is non-zero, which means it'll keep speeding up. So we'll take a snapshot, we'll look at the next delta t. And now, of course, the gravitational force hasn't changed, but because it's going faster, it's running into more air molecules, and so, in fact, this air force got bigger, didn't it? So it depends on speed, and that's going to keep happening until we get to a situation where the force by the air is exactly equal and opposite to the force by the Earth, right? And then at that point, what's the net force on... Yeah, the net force is zero, isn't it? And so at that point, is its momentum going to change anymore? And so the air force can't get any bigger, so that's when it levels off and falls at this constant speed. Right? So we can actually do little experiments to measure approximately what the dependence of this air resistance force on speed would be. So here's the first question in a series of questions to reason through this, and we just answered this question, so I'm not asking it to it. We know that when this falling coffee filter reaches this constant terminal speed, then the net force on it must be zero, and therefore the force by the air must be equal and opposite to the... Okay, now suppose that we, instead of one coffee filter, we take 3 of them, the 3 coffee filters that they're stuck together. So it's basically an object of whose mass is 3 times the mass of one coffee filter, but it's the same shape. Right? And it's still affected by air resistance, but the gravitational force on it is bigger, right? So what's going to be the case with its terminal speed? Terminal speed's going to be bigger too, isn't it? Yeah. And it takes a little longer to reach terminal speed, so if we're going to do this experiment for real, we'd actually want to make sure that we drop them from a fairly as high as we could. So we found that for this one coffee filter, we said that at terminal speed, the force due to the air on the falling coffee filter was F1. For this 3 falling coffee filters, what would we draw here in this force diagram for our 3 falling coffee filters when they reach terminal speed? So here's our Okay, well, the most popular answer is that the air resistance force on the 3 falling coffee filters is 3 times as large. And your reasoning is, that's correct, and your reasoning is probably something like this. Well, the gravitational force on this nest of 3 coffee filters is going to be 3 times as big as it was on 1, so that's the gravitational force. We'll call that Fg1. Fg3 is 3 times Fg1, and therefore in order for the net force to be 0, it must have gotten to a state where the air resistance force is 3 times as large. Well, if we knew how fast it was going compared to how fast the initial one fell, then we could actually we could figure out whether the air resistance force depended was directly proportional to the speed, or the square of the speed, or the square root of the speed, or 1 over the speed, or the... So let's take a hypothetical number, which is roughly reasonable, and see if we can figure this out. So when one filter fell, let's say it fell at terminal speed of 1 meter per second. And when these 3 filters fell, and these are roughly real measurements, when these 3 filters fell, they fell at a terminal speed of 1.7 meters per second, so faster. And we know that the air force is differed by a factor of 3, so how would we write an equation for... What we want to be able to do is write an equation that says the force due to the air is some constant or other which depends on shape times the speed to the something, and that could be a 1/2 or a minus a third or whatever. Okay, so what do we guess here? Well, looking at the textbook isn't actually guessing. So looking at the data. Okay, well, the most popular answer is 4. We've also got a 3. So how do we think about this? How do we use these data to figure this out? This is really a case where proportional reasoning kicks in. And so we've got a situation here where for one filter we have the force of the air on one filter is equal to some constant times 1 meter per second to the something. And we have 3 F air 1 is equal to the same constant times 1.7 meters per second to the something. So what can this exponent be? Well, could it be 1? Well, 1.7 to the 1 is not 3. So it's not just speed, right? Is it going to be negative? No, because that would make it get smaller, not bigger. Well, what about if we tried 2 here? What happens? What's 1.7 squared? 2.9 something. So this comes out to a 2.89. That's pretty close to 3, isn't it? I mean, we're just using one data point, so that's not a very good. So, and it's probably that's probably the closest if you try all those things. What you'd really want, of course, is to get several data points and actually do a fit, but it's suggestive. And this is an empirical relationship. It does turn out it's usually, under most circumstances, it's approximately proportional to the square of the speed. There is a factor in here there's a constant, and then there's a factor that depends on the shape of the object, not very surprisingly. So the force on a blunt object is going to be much greater than the force on a rounded or pointy object. So there's a shape factor. And this is an empirical thing, but the mechanism is this microscopic thing. So if all this energy gets transferred to the air, the Earth is doing work and the filters aren't speeding up. So that work done by the Earth must go into the air. What's happening to the air? And if it's hotter, what's happening at a microscopic level? They're just moving faster. The air molecules are moving faster, aren't they? So we're heating up the air. And what? Sorry, what? Oh, the object being dropped, is it getting hot too? Yes, very probably, because of the collisions with the air molecules, so that the atoms in the object are going to be vibrating also. Yes, definitely. So goes into internal energy of object plus internal energy of the air. So I think you're actually going to do a lab experiment on this in a week.